Alright, hello everyone. I hope you guys are doing good. So today I'll be discussing the solutions to AtCoder Beginner Contest 230. This contest was held yesterday evening, and let's begin by talking about the difficulty levels. So the difficulty was similar to a typical ABC round. The first two or maybe three problems were pretty trivial, and after that the difficulty levels started to increase. The next two problems, D and E, were interesting, and problem F was very good. Like, it was really an amazing problem and it was very thought provoking, right? So all in all, it was a good and well balanced contest, and I will be discussing the first six problems from A to F. So yeah, let's get started with problem A. I'll be skimming through the first three problems since they are really easy. So in this problem, we have been given with the number n, and essentially what we have to do is, if n is greater than or equals to 42, then we have to increment it by 1. Otherwise we don't have to increment it, and we need to simply output the string AGC, and after that we need to output n in 3 digits. For example, if n is 42, then first we increment it by 1 and it becomes 43, and then in 3 digits 43 will be written as 043, right? Similarly, if we have a 3-digit number, it will just be written as it is. If we have a 2-digit number, we will have to add a 0 before that, and if we had a 1-digit number, we'll have to add 2 zeros before that. So yeah, that's the task. So it's pretty simple. We just have to do what's being told to us. Let's just have a quick look at the code. So here what we are doing is, if n is greater than equals to 42, we are incrementing it, and then initially my answer string is just AGC, and if n is less than 10, then I'm adding 2 zeros, and if n is less than 100, then I'm adding 1 zeros. Otherwise, if n is greater than 100, I'm not adding any 0. And finally, I'm just adding n to my answer, and I'm firstly converting n to a string using the toString method in C++, and I'm just appending that to my answer, and that will just work fine. So this completes problem A. Pretty simple. You don't have to think about anything here. So let's now move to the next one, problem B, and here the situation is something like this. So we have been given with a string s, and we have to determine whether so what we have to do is that, given a string s, we have to print yes if s is a substring of t, otherwise we have to print no, right? So that's the problem here, and basically t is something which is being provided to us beforehand. So t is a constant string, and it is a string which is formed by concatenating 10 raised to the power 5 copies of the string oxx, right? That is t. It is fixed. So in the input we'll be provided with s, and we need to tell whether s is a substring of t or not, right? Yeah, so that's the problem, and according to the constraints, the length of s is between 1 and 10. So that's a good thing for us, right? And that's a good thing for us because if the length of a substring is 10, then that means that it is obviously smaller than t, right? So if the length of s is less than equals to 10, it will always be smaller than t, so we don't need to check whether it's greater than t or not. And now simply there are just three possible cases. If the first letter of s is x, then basically there are two possibilities. The string can be of the form xxo xxo xxo, or it can be of the form xox xox xox. And if the first letter is o, then it can just be of the form oxx oxx oxxo, right? So these are the only possibilities. So we just have to form all the three types of possibilities and just check if those strings are equal to s or not, right? So yeah, we'll just have a look at the code for better clarity of what I'm trying to say here. So basically what I'm doing is that there are three possibilities. The three types of strings that I have is oxx, xxo, and xox, right? And I'm checking for all of these three strings, and if any one of the solve functions returns true, then my answer will be yes. And let's have a quick look at the solve function. And here what I'm doing is that first of all, n is the size of my string s1, where s1 is nothing but s, and essentially what's happening is that I know that the size of s2 is 3, so I find out the dividend, and I find out the quotient and remainder when divided by n. So I find n by 3 and n mod 3, and what I do is I append s2 n by 3 times, that is div times, and after that the remainder of the characters will be left, will be n mod 3, and then I add them to my string, and if my string is equal to s1, then I return true, otherwise I return false. So yeah, this is pretty simple. These are just the three possibilities that you have to check, and if either one of them is true, then your answer is going to be yes, otherwise it's going to be no. So yeah, this completes problem B. Let's quickly move on to the third problem. Again, this was a pretty trivial one, although it looked a bit intensive, but it turns out that you didn't have to apply any brains here. So I'll be quickly skimming through this problem. So what's happening here is that we have an n cross n grid where n can be very large. So the thing is that n can be up to 10 to the 18. But first of all of the cells are painted white, and you choose some cells and you paint them black. And you have been provided with the information about which cells you are choosing, right? So you choose an integer k, where k lies between maximum of 1 minus a 1 minus b to minimum of n minus a n minus b, and you paint a plus k comma b plus k black. And then you choose a k which lies between maximum of 1 minus a b minus n to minimum of n minus a b minus 1, and then you paint a plus k comma b minus k black. So you are painting all the cells in these two particular ranges. And finally, you have also been provided with 4 integers p, q, r, s. And what you have to do is you have to output the color of each square I comma j, such that I lies from p to q and j lies from r to s. So essentially you need to print the colors of all the cells in the columns from r to s and in the rows from p to q. And yeah, that's the problem. Initially all the cells are painted white, and a white is being denoted by a dot, and a black color is being denoted by a hash. So yeah, that's what you have to do. And essentially what happens here is that you don't have to apply any brains, even though the constraints are high. Essentially what you can do here is that you need to output all the elements from p to q and from r to s, right? So in the you first loop from p to q and then you loop from r to s. So currently you are at cell I comma j, and you just check that that particular cell I comma j belongs to these two ranges or not. And that is pretty easy to do. Why? Because if there exists a k such that a plus k is equals to I and b plus k is equals to j, and k lies in this particular range, then essentially it's painted black. And in the second case, if there exists a k such that a plus k is equals to I and b minus k is equals to j, and k lies in this particular range, then again it has to be black. And if both of these conditions are false, then it has to be white, right? So yeah, that's what you have to do in this problem. So the first case is that I minus a is equals to j minus b, and if a plus k is equals to I and b plus k is equals to j, then that just means that k is equals to I minus a and k is equals to j minus b. So if I minus a is equals to j minus b, then I know that k is equals to I minus a. So I just have to check whether k belongs to this range or not. So that I do here. So if k belongs to this particular range, then my current character is going to be hash, because the cell is going to be black. And similarly here, if a plus k is equals to I, then k is equals to I minus a. But on the other hand, b minus k has to be equals to j, so k has to be equals to b minus j. So that is why I minus a has to be equals to b minus j. And if that's the case, then k will be I minus a, and I'll simply check whether k belongs to the given range or not. And if that's the case, then my character is going to be black. Otherwise, my character is already going to be white, right? So yeah, this is how you can solve this problem. Pretty easy. You don't have to think about anything here. And this completes the 3 easy problems that we had to discuss. Now let's move on to the 3 difficult ones and interesting ones. So yeah, problem D. This is an interesting problem. So let's see what this problem has to say. So we have a town which is divided into a grid which contains n rows and 10 raised to the power 9 columns. So essentially we have n rows and a lot of columns, and there are n walls. So there is one wall in each particular row, and the ith wall that is in the ith row is from the lth column to the rth column. And this is how the structure is there. So there is one wall in every row, and in the ith row the wall starts from the lith column and goes up till the rith column. And we can look at the figure for better clarity. As you can see here, there are 3 rows and there are 10 raised to power 9 columns, and the first row lies in columns 1 to 2, second lies in columns 4 to 7, and the third lies in columns 5 to 9. Okay, so this is the structure of the problem, and let's see what this problem is asking. So Takahashi has decided to destroy all the n walls. So we have to destroy all the n walls, and what happens is that we are punching the walls, and if we punch a particular wall, we are punching d consecutive columns. That is, if we start our punch from column number x, then all the walls which are from column number x to column number x plus d minus 1 will be completely destroyed. I hope it's clear what I'm trying to say here. So if I punch a wall and I punch at column number x, then any wall which is in between column numbers x to x plus d minus 1 will be completely destroyed. And what that means is that if a wall has any part in the range from x to x plus d minus 1, then it's going to be completely destroyed. So yeah, that's what is happening. And what we need to tell is we need to answer the minimum number of punches that we need to destroy all the walls. So if we try to understand this test case, what's happening here is that here the value of d is 3. So if we punch at the column number 4, then all the walls which are at column number 4 to 4 plus 3 minus 1, that is 6, will be completely destroyed. And what we notice is that these two walls, wall number 2 and wall number 3, lie in that particular range. And that means that they have some part in the range. So the wall number 2 lies in 4 to 7, so it has an intersection with 4 to 6. Similarly, wall number 3 lies in the range 5 to 9, which again has an intersection with 4 to 6. So if I punch at x equals to 4, then both of these walls will be destroyed, and then I'll be left with just one wall which can be destroyed with another punch. And hence the answer to this test case is 2. So I hope the problem is clear, and let's try to solve this problem by making some observations. So this is a very typical class of problems. There have been many related problems like this, and the first thing that you should do when you encounter such a problem is always think about sorting. Right, so the first thing that you have to do is you have to think about sorting the array. But a question arises that in this problem you have been given two values for every row, right? A L value and an R value. So the question arises naturally that whether you sort the array based on L values or you sort the arrays based on R values. That is, whether you sort based on starting point or the ending points. So as I said, this is a very typical class of problems, and in such class of problems, you have to basically decide whether you have to sort based on L or R. So what you have to do is you have to try to analyze sorting based on which dimension is going to help in formulating a valid greedy algorithm. So what you have to do is you have to try to analyze that, okay, if I sort based on L values, will there be a valid greedy algorithm that will surely work? Or if I sort based on R values, will there be a valid greedy algorithm? And in this case, it turns out that we need to sort based on R values. And if we do that, then there is surely going to be a valid greedy algorithm that's going to work. So if you try to sort based on L, you will realize that there will be some flaws. So let's try to see why sorting based on R will be correct. So what happens is that there are a few intervals, right? So let's say I sort all these intervals based on R values, and this is the first interval. Now, this is the first interval, meaning that this is the interval which has the smallest R value. That is, there is no interval which is ending to the left of this point, this particular point. Now, since I have to destroy all these walls, I have to destroy this wall as well, right? And what will be the best way to destroy this wall? I mean, obviously, if I hit anywhere in the range starting from, let's say this point is A and this point is B, then if I hit anywhere in the range from here to here, I will be good, right? Where this distance is D. So this distance is D. So what I'm trying to say here is that I know that if I hit at a particular point x, then every point in the range from x to x plus d minus 1 is going to be affected. So if I hit here, then this wall is going to be broken, and if I hit here, then again this wall is going to be broken. But which of them is the best choice? And obviously the best choice is to hit at x equals to b, and that is because if I hit at this point, then I will have this particular distance of d, and if there is any other wall which is in this region, then it will also be destroyed, right? And I know that all the walls have their ending points which are greater than b. So what that means is that there is no wall which ends before b, and hence it makes sense to hit at x equals to b, because there is no wall which ends before x equals to b. So all the walls are ending after x equals to b, and what that means is that if there is a wall which is starting before x equals to b, even that is ending after x equals to b, and that is happening because I have sorted my array based on the r values. And so if it is my first element, I know that there is no wall which is ending before x equals to b, so it is beneficial if I hit at x equals to b, because in that case I will be able to destroy all the walls which have any part in the region from x equals to b to x equals to b plus d minus 1 as well. And I am sure that this algorithm is correct because there is nothing which is stopping me from doing it, and it is also the most beneficial thing to do. And so what we realize is that sorting based on r values gives us a very valid greedy algorithm, right? So yeah, this is how things are going to work here. So what we realize is that sorting based on r is giving a valid greedy algorithm. Again, if you try to sort based on L values, you'll realize that the thing which you are doing is not actually optimal. But here there is nothing which is contradicting you, because you know that there is no wall which is ending before x equals to b. All the walls are still alive. So if you are at the first element, you know that other than the first wall, all the walls are still alive beyond x equals to b. So it's beneficial that I hit this wall, but I hit it at x equals to b, because then I will be able to destroy all the walls which lie in the interval from x equals to b to x equals to b plus d minus 1 as well. So this basically completes the solution. What you are going to do is you are going to hit the wall at x equals to b, and then you'll go to the next wall, and when you realize that this next wall lies in the interval from x equals to b to x equals to b plus d minus 1, and that means that it has an intersection with the interval from b to b plus d minus 1, then you will just skip that wall because it has already been destroyed by the previous shot. And you will keep skipping the walls until and unless there is a wall whose intersection with x equals to b plus d minus 1 is 0. That is, it is null. So what I'm trying to say is that if after sorting, if the first wall lies in a to b, then it is optimal to punch at x equals to b, because after doing this, any wall which lies in the interval, so any wall which lies in the interval from b to b plus d minus 1, b to b plus d minus 1 will also be destroyed. And you can just keep repeating this process and then basically get done with the solution, and you'll be sure that this greedy algorithm will give correct results. And that's because if you hit at x equals to b, you know that there is no wall which has already been finished, right? Every wall is being finished after x equals to b. So you know that all the other walls are still alive or they have not yet started. So it's beneficial to sort based on r values other than L values here. I hope this is clear. A lot of people actually asked me after this round why we are sorting based on R values and not L values. And the reason for that is that if we sort based on R values, we know that if we are looking at the first wall, all the other walls are either yet alive or they have not yet started. And so if we hit at x equals to b, it will be the most beneficial thing for us to do. And that's the reason we are sorting based on R and not L. So yeah, this completes the solution. You just keep doing this. If you find a wall which is in the region from b to b plus d minus 1, you skip it. Otherwise, you hit at the end of that wall and you just keep repeating the process. So let's just have a look at the code now. So yeah, I am taking a vector of pairs and I am sorting based on r values. As you can see, I am first of all taking ai dot second and then I am taking ai dot first. So ai dot second is denoting L and ai dot first is denoting R. So I am sorting based on r values. And I am keeping an interval which is initially 0, 0, and this interval is nothing but b to b plus d minus 1. And once I realized that my current wall has zero intersection with that interval, and the condition for zero intersection is this: either its starting is before the ending of the interval or its ending is after the starting, then that means it has zero intersection with my interval. So if it has a zero intersection, then that particular wall has not yet been destroyed, and I destroy that. And once I destroy that, my interval becomes the ending of my current wall to the ending of my current wall plus d minus 1. As you can see here, the interval becomes b to b plus d minus 1, and b is nothing but ai dot first. So my new interval becomes ai dot first to ai dot first plus d minus 1. And in this way, in O of n log n, we have successfully solved the problem based on this greedy algorithm. So I hope you guys were able to understand what exactly is happening here. So, and this completes the solution to problem D. Moving on, let's now talk about problem E, another interesting and simple problem. Well, very short and concise problem. You have been provided with a positive integer n, and you have to compute this value. Simple. And that is one thing which is very good about AtCoder. There are no unnecessary stories here. You have very straightforward problem statements. So yeah, you have to find out for a given n the value of this summation, which is I going from 1 to n, the floor of n upon I. And by floor, I mean the greatest integer function. Let's see how to solve this problem. Okay, so this problem says given n, find n by 1 plus n by 2 plus n by 3 up till n upon n. So this is the required expression that we need to find. So let's start by making initial easy observation, and let's say that this sum is s, and the observation that I'm going to make is that every element here, that n upon I, so we need to find summation of n upon I, right? So we need to find for all I sum of n upon I, right? That is what we need to find. So the first observation is that n by I obviously lies between 1 to n, right? So n by I obviously lies between 1 to n. So also here, if you look at the constraints, they are really large. The value of n goes up to 10 to the 12. So obviously we can't just naively compute the sum, because that will give us a time limit exceeded. But yeah, the first observation is that n by I lies between 1 to n. That is pretty easy to see because it is a non-increasing function, and for I is equals to 1 we get n, and for I is equals to n we get 1. So naturally the value n by I lies between 1 to n for all values of I. And let's try to break this solution down. Given n is equals to 10 to the 12, we wonder what can be the time complexity of the solution. One might think that we would need an O of log n solution, but then again, if we were required to give an O of log n solution, there was no reason for the problem setters to give n up to 10 to the 12. Like, they could have easily given n up to 10 to the 18, as it is done in most of the problems. So this is a good hint that they haven't given n up to 10 to the 18 but up to 10 to the 12 for a specific reason, and that reason is that they might be expecting from us an O of square root of n solution, and that's why they haven't given a very huge n, and they have given a reasonably large n. So that's the first hint that leads us to thinking about root of n. Because n is up to 10 to the 12, root of n is 10 to the 6, which is good enough. So why think about a log n solution when you can think about a square root of n solution? So this is the first hint, and this is how we start thinking about square root of n. So let's say k naught is equals to square root of n. So sqrt of n is the standard sqrt function which gives us the floor of the square root of n. So let's say k naught is equal to the floor of the square root of n, the greatest integer of the square root of n. Now, what we'll do is, for all values from 1 to k naught, we'll try to find the contribution of each value. So for each value of k from 1 to k naught, we will find the number of terms n by I such that n by I is equals to k naught. no, n by I is equals to k. Now pay attention, I'm only going from 1 to k naught. I know that these terms will go from 1 to n. So I'm breaking down my solution into two parts. The first part is for those values which are from 1 to k naught. And the second part is for those values which are greater than k naught. That is from k naught plus 1 to n. So if I, for any value of k, if I try to find the number of i's such that n by I is equals to k, then if that particular number is x, then I know that the contribution is k is going to be k times x, right? So let's try to find out the value x for all the values of k from 1 to k naught. Now I know that the floor function of n by I will be k if and only if n by I is greater than equals to k and n by I is strictly less than k plus 1, right? Because if n by I is greater than or equals to k plus 1, then the greatest integer function of n by I becomes k plus 1. And so this is a necessary condition for the greatest integer function of n by I to be equal to k. And from this, what we can conclude is that if we cross multiply, we'll realize that I has to be less than or equals to n by k and I has to be strictly greater than n upon k plus 1. And if these two conditions are satisfied, then and only then n by I, the floor function of n by I is going to be k. So the number of I such that the floor of n by I is equals to k is equals to nothing but n by k minus n by k plus 1. And that's pretty easy to see from these two inequalities, because we know that I has to be less than equals to n by k and I has to be strictly greater than n by k plus 1. So the number of such I is naturally n by k minus n upon k plus 1. So the first part of our answer is going to be like this. It's going to be summation of k times n by k minus n by k plus 1 for all k. So for all k from 1 to k naught, right? Because I'm only considering numbers from 1 to k naught. This is the part 1 of my solution, where the values n by I can only range from 1 to k naught, and I have calculated the contribution of each of them, and I know that k naught is square root of n, which is up to 10 to the 6, which is not a very big number and which will fit in my time limit. So I can naively iterate from 1 to k naught and find out this sum. Now what if the value of n by I becomes greater than k naught? So what I'm trying to say is the value n by I becomes greater than or equals to k naught plus 1. Well, the good thing here is that we have broken down the solution into two parts. We have already calculated the first part, and it seems that the second part is also very easily calculatable. And that's because if I know that n by I is greater than equals to k naught plus 1, what that means is I is less than equals to n upon k naught plus 1. And we know that k naught is nothing but square root of n. So this term is nothing but n upon square root of n plus 1, which is around square root of n only, right? So this is also about square root of n only. So what I can do is I can naively iterate from 1 to n by k naught plus 1 and find out this value. What I'm trying to say is, so we can naively iterate from 1 to k naught plus 1 and add n by I to the answer. I know that I has to be less than equals to n upon k naught plus 1. So I can simply iterate from 1 to n upon k naught plus 1, n upon k naught plus 1, and add n by I to the answer. And this will straight away give me the second part of my answer. So this is the first part of my answer. And if we talk about the second part of my answer, it's going to be nothing but I going from 1 to n upon k naught plus 1 summation of n over I. So yeah, these are the two parts of my answer, and that will just give me the correct answer. So let's just have a look at the code. This completes the solution. Essentially, we are breaking down the answer into two parts. One where the value of n by I is strictly less than root of n, and one where it is greater than equals to root of n plus 1. So this is the first part. My I is going from 1 to k naught, and I am adding I times n by I minus n by I plus 1 to my answer. And the second part is that I am naively going from 1 to n upon k naught plus 1 and adding n by I to my answer. So this way, in O of square root of n, I have computed the correct answer, and this works. So yeah, this completes problem E. Very interesting problem. Now let's move to the last problem that we'll be discussing today, and trust me, this is a very elegant and very good problem, and it's really a thought-provoking problem, right? So let's see what this problem has to say. So we are given a sequence A of length n, and we can do an operation any number of times. What we'll do is we'll choose two consecutive adjacent integers, two consecutive adjacent values in the sequence, add them, and replace those two numbers with their sum. This is a very standard operation. A lot of problems do this operation, but this is a very unique problem because in this problem, what we have to tell is we have to count how many sequences, that is, how many distinct sequences that can result by doing 0 or more operations. So yeah, that's the problem. We have to count it modulo this number. N can be up to 2 into 10 to the 5, and the numbers ai can be up to 10 to the 9. This is the problem. So in an operation, we can choose two adjacent numbers, add them, and replace those two numbers with their sum, and we need to tell what is the number of distinct sequences that will be formed. That's the problem, and let's try to see how to solve this problem. I had a lot of fun trying to solve this problem, so definitely I would recommend trying out this problem. It's a very nice fun. Okay, so let's start with making a initial observation, and let's see what's happening. So let's look at this sample input. Here n is equals to 3 and the answer is 4, and this looks suspicious because 4 is nothing but 2 raised to the power 2, right? And let's see how the answer can be 2 raised to the power n minus 1 always, or whether it's the case or not. Obviously it's not the case because n is equals to 10 and 2 raised to the power 9 is 512, but here the answer is 321, so it's obviously wrong. But let's see where the intuition of 2 raised to the power n minus 1 is coming from. So for every pair I comma I plus 1, we have a choice of either merging I and I plus 1 or not merging them, right? So let's try to formulate this. So for each pair I comma I plus 1, we have a choice of either merging this pair or not merging, right? And the number of such pairs is obviously n minus 1 because I can go from 1 to n minus 1, and hence in the first look, in the first observation, it looks like answer is nothing but 2 raised to the power n minus 1, because we have a choice for any pair I comma I plus 1. We will either merge it or not merge it, and there are n minus 1 such pairs. So why is the answer not always 2 raised to the power n minus 1? Well, it's well and good for the first test case, but when you look at the second sample, this analogy fails. And let's see the reason for that. So let's look at an example, and that will make things very clear. So let's look at an example of this sequence: 1 minus 1 1 minus 1. In the first test case, we have just 1 minus 1 and 1, and the answer is perfectly fine, 2 raised to the power n minus 1, and nothing's wrong there. But if you try to find all the sequences that you can make from this, you will realize that the answer here is 7 and not 8, where 8 is 2 raised to the power 3, right? And let's see why that is happening. So what happens is that once we notice this thing, that the sum of the second and third numbers here is 0. So to begin with, we had a sequence 1 minus 1 1 minus 1, and let's say we merge these two numbers. We do an operation on the second and third number and we merge them. So now this becomes 1 0 1, right? And now the tricky part is that let's say we decide to merge this 0 and 1, and so we had 1 0 1, right? And we decide to merge the merge a1 and a2, and in that case we will get 1 comma 1. But we can also decide to merge a2 and a3, right? So we had 1 0 1, and if we decide to merge a2 and a3, we will again get a 1 comma 1. And the problem asks us to find the number of distinct sequences, right? 1 comma 1 and 1 comma 1 are the same sequences. So it turns out that if we just simply do 2 raised to power n minus 1, we will be overcounting, and we will be overcounting these two sequences. So we'll be counting 1 comma 1 twice, and that's why we have to decrease the answer by 1, and that is why the answer to this test case is 7 and not 8, because we are overcounting the sequence 1 comma 1, and that's why the answer is 7 and not 8. So it turns out that there will be recurring sequences which we need to remove, right? So in an ideal world, if there were no recurring sequences, then we can just simply say that the answer is 2 raised to power n minus 1. Or if we try to apply dynamic programming, there would have been a very simple recurrence relation, that is dp of I is equals to 2 times dp of I minus 1, where dp of I is nothing but the number of sequences that can be formed from the first I numbers. And that's because if we have any sequence which is formed from the first I minus 1 numbers, I can either append a of I to the right of it, or I can add a of I to the last element of it. So I have two choices, and that's why dp of I would have been 2 times dp of I minus 1. Let's try to formulate it. So if we denote, first of all, we will use dynamic programming to solve the problem. That's the first thing. And now the problem here is that there will be recurring sequences which we have to remove, right? And for now, let's forget about recurring sequences. If there were no recurring sequences, if we denote by dp of I, so dp of I is equals to the number of sequences formed from the prefix of length I. And if there were no recurring sequences, so if there were no recurring sequences, then we can simply say that dp of I would have been 2 times dp of I minus 1. And the reason for that is that for any sequence which is ending at I minus 1, I can either append a of I to the end of it, or I can either add a of I to the last element of it. That's why dp of I would be 2 times dp of I minus 1, and this would simply lead to dp of n is equals to 2 raised to the power n minus 1. And we have already proved that that is the wrong answer, because there will be recurring sequences. Also, the final answer here is obviously going to be dp of n. So our task is to remove recurring sequences. Right. And here we saw that once we find a subarray such that its sum is 0, that subarray, if we combine it, it can be either combined with the left sequence, or it can also be combined to the right sequence. So what I'm trying to say is that this 1 and minus 1 sum up to 0, and this 0 can either be combined with the left element or to the right element as well. And both of them will give the same result, because at the end of the day it's a 0, and if I'm adding it to some 1, it won't change its value, right? So this 1 will stay 1, this 1 will stay 1. And that is where the recurring sequences are coming from. And so the only way I am getting recurring sequences is from subarrays whose sum is 0. So let's write that down as well. The only way we are getting recurring sequences is through subarrays whose sum is 0. Because for these subarrays, I can either combine them with the left sequence, with the sequence to the left of it, or to the sequence to the right of it, right? So yeah, now again, this dp of I, the definition of dp of I is same, but we'll try to make transitions in a different manner. Obviously, dp of I will be 2 times dp of I minus 1. So dp of I is equals to 2 times dp of I minus 1 minus extra recurring sequences. Extra recurring sequences introduced by the ith element. And if we do this, then the dp of I will start representing the number of distinct sequences which are formed from the prefix of length I. So first we'll do dp of I is equals to 2 times dp of I minus 1, and from that we will subtract the extra recurring sequences which are being introduced because of the ith element. Okay, great. Now let's see where these extra sequences are getting introduced. So I'm starting from 1, and let's say there is an element j, and then there is I minus 1, and then there is I. And I want to calculate dp of I minus 1, and obviously you might be wondering what this j is, so let's define it as well. So let's say that j is the rightmost such element such that the sum of the elements in j plus 1 to I minus 1 is going to be 0. So what I'm trying to say here is that, let's write it down here. So j is the rightmost element such that the sum in the range from j plus 1 to I minus 1 is 0, right? And obviously, if this is subarray whose sum is 0, this is the only subarray which is introducing the extra recurring sequences, because all the other recurring sequences have already been encountered by dp of I minus 1 and they have already been reduced. And I have to count the extra recurring sequences which have been introduced due to the addition of the ith element, and I have to subtract them from 2 times dp of I minus 1. And so obviously all of these extra recurring sequences will be introduced by this subarray which is starting from j plus 1 and going till I minus 1, right? So obviously if the sum of this subarray is 0, then what that means is that the prefix sum of j is equal to the prefix sum of I minus 1, right? That is again another natural thing. If that's the case, then and only then the sum of the subarray j plus 1 to I minus 1 is going to be 0. Cool. So yeah, I know that prefix sum of j is equals to prefix sum of I minus 1, and if that is the case, then I need to find the rightmost such index j, and if I successfully find that out, then I know that the extra recurring sequences are being introduced only by the subarray which is starting from j plus 1 to I minus 1. And I need to count the number of these extra recurring sequences and just subtract them from 2 times dp of I minus 1, and if I do that, I will get my correct transitions, right? And we need to find the number of recurring sequences introduced through the subarray j plus 1 to I minus 1. And I know that every subarray which has a sum of 0 is introducing some extra sequences which are recurring, and that's because now let's see what's happening. So this particular 0, again, it can be combined with the last element. It can be, so it has two choices. This 0 has two choices. It can be combined with the last element in the sequence which is being formed through 1 to j, or it can be combined with a of I, right? So let's write that down as well. So the 0 can be combined with either the last element of sequence formed in the prefix of length j, or it can be combined with just a of I, right? And these are the two cases. And obviously if I'm combining it with a sequence of length j, there has to be a sequence of length j, right? And the number of such sequences are nothing but dp of j. So that's why the number of such extra recurring sequences introduced by subarray j plus 1 to I minus 1 is nothing but dp of j. And that's because I need a sequence which is being formed by the prefix of length j, and if I combine this 0 with that sequence and then I add ai to the end of it, or if I combine this 0 with a of I, or add that at the end of it, both of the formed sequences are going to be the same, and hence the number of extra recurring sequences that are being introduced is nothing but dp of j. If it is not clear, I'm going to explain it once again. So I have this sequence from 1 to j, right? I have a sequence which is getting formed from 1 to j, and I have this 0. So let's say I combine this 0 with the last element of the sequence and nothing changes, right? So this 0 is combined with the last element of the sequence formed through 1 to j, and now I'm left with a of I, and so I add a of I here. So this is the sequence which will be formed. And the second choice for me is that I have this sequence from 1 to j, and what I do is I add this 0, I combine this 0 to a of I, and then I append a of I to the right of this sequence. Again, in that case, I'll be left with a of I. And as you can notice, both of these sequences are just the same, and that is why this is a recurring sequence which is being introduced through the subarray j plus 1 to I minus 1, and the number of such sequences is going to be nothing but dp of j, where dp of j is the total number of distinct sequences which are being formed from the prefix of length j. And that is why the number of extra recurring sequences is nothing but dp of j, and so my transition becomes easy, which is dp of I is equals to 2 times dp of I minus 1 minus dp of j, where j is the rightmost index such that prefix sum of j is equals to prefix sum of I minus 1, and that's the case where the sum of the subarray from j plus 1 to I minus 1 is going to be 0. Phew. So yeah, this completes the solution, but there is just one problem. How do we actually find out j? And that's not a very difficult thing to do. We can just keep a map, and we will just keep updating a map, and yeah, we can keep a map for all the values of prefix sum. And since we know that there are at max 2 into 10 raised power 5 values, even though those values will be around 10 to the 9, it doesn't matter because I'm keeping a map, and I can just keep a map for all the values of prefix sums to find out their dp values. And using map, I can easily find out the value of j for each value of I, and I can make my transitions. So let's just have a look at the code to get some better clarity. If you were not able to understand how we are actually finding j, I'm sure looking at the code is going to help. So I'm keeping a map called pre, and I'm keeping a dp array. Obviously dp of 1 is equals to 1, and initially my prefix sum is nothing but a of 1. Then I go from 2 to n, and I first do dp of I is equals to 2 times dp of I minus 1. That's cool, but I know that my prefix sum of I minus 1 is nothing but sum, right? I'm maintaining the invariant that sum is always prefix sum of I minus 1, and so I will subtract pre of sum. So pre of sum is nothing but the dp value of j such that prefix sum of j is equals to sum, right? Yeah, I guess it is easily understandable here what I'm trying to do. So I'm just subtracting pre of sum, where pre of sum is nothing but dp of j, where prefix sum of j is equals to sum, and sum is nothing but prefix sum of I minus 1. So essentially pre of sum is nothing but dp of j such that dp of j is equals to prefix such that prefix sum of j is equals to prefix sum of I minus 1. And once I do that, I don't have to forget that I also have to keep this map updated. So I will do pre of sum is equals to dp of I minus 1, and then I will increment my sum. So this way I am always keeping this map updated, and using this I can easily find the value j for all the values I, and I can just subtract pre of sum from dp of I, and keep updating my sum and keep updating my map as well. And finally my answer is going to be dp of n. And yeah, so as you can realize that the code is very small, but the problem is really elegant. So it was just a very good problem. So this completes the solution to problem F. So yeah, thank you for watching the entire video, and I'll see you in the next one. Bye bye.